Okay, so we have day 8. We're just starting to talk about friction. So our first friction problem, we have a block like so that is sitting on a frictional surface. And this block is attached through some frictionless pulley to another block which is just hanging in thin air. We know that this block right here has a mass of 10 kilograms, and we know that this block right here has a mass of 7 kilograms. And we want to know a few things. The other thing we know before I get to that is I have my coefficients of friction for the surface between the interface between the block and the ground. So I have a coefficient of static friction, which is going to be equal to 0.60, and I have a coefficient of kinetic friction, which is going to be 0.50. Okay, sorry, those are a little bit off the board there. So I've got my inputs there. What I want to know from this, so my what defines, making sure I keep as much as I can on this board. And what defines? I want to know, does it move? If I don't give it a yank or anything, will it naturally start moving from just having that 7 kilogram block there? Is that 7 kilogram block enough in order to make it start moving? Then the second thing I want to know is, regardless of whether it's enough, we can always give it a little yank so it gets going. We move from our static condition to our kinetic condition. And once it starts moving, we want to know what my friction force is, and we want to know what my acceleration is. So I'm after 3 things that I'm trying to solve for here. Okay. Let's get started. First piece that I want to do is I want to solve for these blocks, and I want to get my free body diagrams drawn for these blocks to understand what exactly is going on. So I'm going to start with this guy. I'm actually going to call him block 2. But block 2 has a upwards tension, and it is going to have a downwards gravitational force. So mass of block 2 times gravity. That's all that's going on with block 2. It's just a hanging block. Block 1, on the other hand, which is what I'm going to call this block right here. Block 1 has the tension, and you notice that I'm marking them both as T. It's again that rope idea. If I'm pulling on one rope and on one end and the other end, I have to be pulling the same length or it's going to start stretching and deforming. Kind of idea of if this guy starts moving, it's going to have to stay the same length. We're going to figure that out. We'll talk about that in a second. Other pieces I have going on with this, I have my mass of block 1 times gravity, and I have my friction that I know has to happen. Last piece that is missing here is, if this were my free body diagram, there's nothing to keep it from just going straight through the surface. It would just fall infinitely. So I need some form of normal force such that it is not going through the floor, which is not an ideal condition. So how am I going to do this is we're going to now start drawing our free body diagrams. I know I've kind of drawn it on here. This is probably fairly acceptable, but these aren't technically free body diagrams. So I'm going to do my free body diagram of block 1. It's going to look like this little cube. We're going to have a mass of 1 times gravity going down. We're going to have a normal force going up. We're going to have tension going to the right. We're going to have a friction going to the left. And that is off the page, so let me rewrite the friction. There we go. And then if we look at block 2, and I do a free body diagram for block 2, and I draw my block in here, I have mass of block 2 times gravity going down, and I have a tension going up. All that's left is direction. Now, if we think about what's going on here, when we get to the second condition, we start moving. Acceleration is going to happen in this direction. Acceleration is going to happen in this direction. And those accelerations are going to have to be the same. This is where I was saying that movement of one side of the rope has to be movement of the other. If this rope isn't stretching or compressing, if this block moves over 2 inches, this block is going to have to move down 2 inches because the rope needs to stay the same length, which means the acceleration of block 1 should be equal to the acceleration of block 2 for anything we're going to be doing in this class. So with that, if we were to call this our coordinate system and we said positive y is up, positive x is to the right. This is a different color. You'll have to believe me. I know the green and yellow look very similar. What might make sense is to make it so that positive x is to downwards in this guy, which makes things a little bit easier to think about. We don't have the fact that things are reversing going on here. That is probably how I have it in the notes, and that's probably how I'm going to approach it in class. I'm going to go ahead and, for the video, approach it such that positive y is up and positive x is to the right. It's going to make very little difference here. We just have to go through a few thought experiments in order to get things together. Okay, let's start with our first condition, and I'm going to get a different color out here. My first condition, I have my is, and that's off the board. I have my is it moving condition. This condition is right before the block physically starts moving. And what we're going to do for it is we're going to say acceleration is going to be, like where it first starts moving, it's going to be very, very, very small. So we're going to treat it, in this case, as we figure out what's going on, we're going to treat it as acceleration of 0. So in this condition, if I look at block 2, I can say that my sum of my forces in my y direction are going to be equal to my tension. Well, so it's going to be equal to the mass of block 2 times my acceleration in the y of block 2. And I'm saying my acceleration is very, very small. We're going to treat it as 0. So sum of forces is equal to 0. And my forces are my tension minus the mass of block 2 times my gravitational constant is going to be equal to 0. Or it's going to be very, very small. So if it is equal to 0, it's not going to move. But we'll get there in a second. So we have my tension is going to be equal to mass of block 2 times my gravitational constant, which is going to be mass of block 2 is 7 kilograms times 9.81 meters per second squared. And that number comes out to be 68.67 newtons. So if it's not moving, my tension is 68.67 newtons. Let's see if that tension is enough to overcome friction, we're going to go ahead and switch, and we're going to talk about block 1, our main block in this problem. For block 1, we're going to have to break this into my x and y axes. In my y-axis, I'm going to say my sum of forces in the y is going to be equal to the mass of block 1 times my acceleration in the y. In this case, not only are we assuming the acceleration is very, very small, going up and down the acceleration truly is 0. So sum of forces in the y has got to be equal to 0, which means normal force minus the mass of block 1 times gravity is going to be equal to 0. My normal force is going to be equal to the mass of block 1, which is 10 kilograms, times 9.81 meters per second squared. It's going to be 98.1 newtons. That is my normal force. Now, if I look at my x-axis, I have my sum of my forces in the x is going to be equal to my mass 1 times my acceleration in the x. This is where we actually have to think about this a little bit. So in this case, we're trying to say that if we set this to 0, the sum of my forces in the x, if this number comes out and this number is equal to 0, we're right at the point where like you could just spit on this thing and it would start moving. If it ends up being greater than 0, then we have the condition where we are physically going to move for sure. If we are less than 0, we're not actually going to move, and we have to have sum of forces is equal to 0, so we actually have less friction than we're calculating. And we'll get to that in a second too. So in this case, sum of forces in the x are going to be positive tension minus my force of friction, static, is going to be equal to 0. So in this case, for it not to move, tension has got to be equal to my static friction. That is the not moving condition. If tension is greater than the force of static friction, then what's going to happen is it is going to move. If the force of static friction is greater than the tension, not only is it not going to move, then this is not actually my force of static friction. Because if we recall, my force of static friction equation is force of static friction is going to be less than or equal to my coefficient of static friction times my normal force. And the reason that I have this less than or equal to is because if I set this block, I just set it down on my surface, there is no friction force. Friction only opposes movement. So, but there is a normal force, and there is a coefficient for static friction. So if we plug it into this equation, it's not going to come out to be 0. And we want it to come out to be 0. So force of static friction is whatever it needs to be up to this number. It cannot be larger than this number. So something to keep in mind and keep track of as we think about this. Force of static friction, we have that less than or equal to symbol in here. Okay, let's solve it. So force of static friction, we just said that is going to be, tension is going to be equal to my mu static times my normal force. And we're trying to figure out, we're trying to answer this question. So I'm just going to go ahead and replace this 0 with a question mark. My tension is 68.67 newtons, which is somehow related to my mu s, which is 0.6, times my normal force, which is 98.1 newtons. This number ends up being 58.86 newtons, meaning that my tension is greater than my maximum force of static friction. And since that is the case, if these blocks were just sitting here, they would start to move because this guy has enough force, it's going to create enough tension that everything is going to start to slide. We solve for it as if this were 0, but in reality there is going to be some acceleration there because we're breaking the limit of how much the friction can actually hold. The friction can be so strong, and we have overcome it with this weight. Now I'm going to go ahead and pause and let myself clean all of this board off so we get a little bit cleaner board for the second half of this video. Okay, voila, we have determined that yes, in fact, it does move. So with that, we're on to our next condition, which is our moving condition. So we now have a moving part. So we're going to first start, again, by solving for our second piece, just because this is going to be our easier equation. We don't have to deal with anything in the x. We don't have to deal with any friction. Let's knock out the low-hanging fruit first. So with this, what we know is our sum of our forces in the y direction are going to be equal to our mass times our acceleration. This is the mass of block 2. This is the acceleration of block 2 in the y direction. So acceleration of block 2 in the y direction is no longer equal to 0 because we are moving, we are accelerating. So this guy doesn't go away. What we get is our free body diagram has stayed the same. We still have tension going up. We have mass of 2 times gravity going down, and this is equal to mass of 2 times acceleration of 2 in the y direction. Okay? Which means that we now cannot quite solve this because we have two unknowns. We don't know what the tension is, and we don't know what our acceleration of 2 in the y is. So what I'm going to do is I'm going to write this I'm going to solve it for tension. I'm going to say that my tension is going to be equal to my mass of object 2 times gravity plus my mass of object 2 times my acceleration of object 2 in the y. And we will get back to that. We now have that condition, so we know this is here, but we don't have enough information to solve it. We're going to need to move to our second set of data, or our second block in this case. And our second block, once again, what we're going to do is we're going to need x and y. So we have our x-axis, we have our y-axis, and we'll go down. Let's start with the y. Sum of forces in the y is going to be equal to mass of 1, acceleration of 1 in the y. Acceleration of 1 in the y, it is accelerating to the right here. It is not going up and down. This guy remains equal to 0. Sum of forces is just going to be normal minus mass of object 1 times gravity is equal to 0. I can still say my normal is going to be equal to my mass, which was 10 kilograms, times 9.81 meters per second squared is going to be equal to 98.1 newtons. Okay? We have our normal force. Now that we have our normal force, we can start talking about what's going on in the x. And within the x, we have our sum of forces in the x is going to be equal to mass of block 1 times acceleration of block 1 in the x. Okay? And the sum of our forces, we have a tension in the positive direction, and we have a friction in the negative direction. And our acceleration is not 0. So we're set up like this. And our tension, well, I can go ahead and put in our tension as our mass of 2 times gravity plus the mass of 2 times acceleration of 2 in the y. So that whole thing we said is equal to tension. And then minus our frictional force. Well, our frictional force when we're moving is mu k times n, and that one is truly just force friction k is equal to mu k times n. There's no greater than, less than, equal to, whatever. It's just straight up equal. So with that whole thing has got to be equal to m1 times a1 in the x. And with this, what we're seeing is we have mass 2. We have gravity. We have mass 2. We want acceleration of 2 in the y. We have mu k. We have our normal force. We have our mass 1. We have our acceleration 1 in the x. We do not have either of these accelerations, though. Sorry. So we don't have acceleration 2 in the y. We don't have acceleration 1 in the x. Well, what's happening here is these guys are actually related to each other. We talked about it before. If we're moving our line 1 inch to the right, this is going to move down. So acceleration in the x is just going to be acceleration in the y. Except we set it up so when this acceleration is positive, this acceleration is negative, which means I'm going to have to mess with some signs here. So what I'm going to do is I'm going to just call acceleration of block 1 is just going to be my acceleration, which means the acceleration of block 1 is going to be the same as acceleration of block 2, except the one change that we have, this is not erasing only what I want, is we have a negative sign there. Now we have one equation, one unknown. I can go ahead and extract both of the accelerations to the other side. So mass of 2 times gravity minus mu k times my normal force is going to be equal to mass of 1 times acceleration plus my mass of 2 times acceleration. I added this to the other side. I get my mass of 2 times gravity minus mu k times n all over mass 1 plus mass 2 is going to be equal to acceleration. I know you guys probably already plugged in your numbers in here by now. I haven't, so let's go ahead and do that now. It's no problem if you plugged them in already. My mass of block 2 is going to be a mass of 7 kilograms. My gravity is 9.81 meters per second squared. My mu k is 0.5. My normal force is 98.1 newtons. My mass 1 is 10 kilograms plus 7 kilograms. I've got 7 times 9.81 minus half of 98.1 divided by 10 plus 7 is going to be my value. And I do believe I already have that calculated. I get my acceleration is going to be equal to 1.154 meters per second squared. So I have my acceleration. Now I noticed partway through this, I'm going to erase the middle just so my face isn't behind a bunch of stuff. Notice halfway through this that I did skip my force of friction. Well, my force of friction is super easy. We actually wrote up the equation up here earlier, we just never solved it. We said our force of kinetic friction is just going to be equal to our coefficient of kinetic friction times our normal force. I have my normal force, I have my kinetic friction. This guy is going to be equal to 0.5 times 98.1 newtons. Half of 98.1 should be 49.05 newtons. So the only thing that I really needed for that is I just need to do my calculation in the y, and then I can get that frictional force. And didn't do anything silly there. I don't think I actually ever solved for it in my notes. But there we go. We have solved for all three of these. A little bit long, hopefully nothing too complicated. If it is a lot easier for you, start throwing numbers in early so you only have the variables you don't know, and maybe that is a little easier to keep track of. I would recommend trying to keep track of units. It's a great way to double check and make sure you don't make any silly mistakes, but I understand if that's not your style. Take care.